Warm regards to everyone. My name is Pallavi Aggarwal. I'm working as a postdoctoral fellow in the Department of Electrical Engineering. Today, I'll be giving a presentation highlighting why my research is important. The title of my research is 2D Materials as Enablers of Next Generation Neuromorphic Hardware. This slide, I'll discuss about the age of semiconductors and rise in humanoids. This image highlights a collaborative robot outlook 2030, emphasizing the growing partnership between humans and robots. It shows how collaborative robots, that is, cobots, are transforming industries through greater flexibility, artificial intelligence, and Internet of Things integration, and a very safer human-robot interaction. This graphics also points to the expanding application for small and medium enterprises, improved productivity, and a future market led by rapid technological process and widespread global adoption. However, majority of the present-day robots, or I should say cobots, are based on von Neumann architecture, which limits their processing abilities such as real-time perception, learning, decision-making, especially for sensor-rich tasks. This is evident from the structure of the von Neumann architecture. In this architecture, basically, the memory and processing units are physically separated from each other. The data and instructions are shared in the memory unit, while their processing takes place at the central processing unit, which is CPU. This results in shuttling of the data back and forth between the memory and processing units and results in high energy consumption, latency, and restricted memory handling capacity. For the idea of cobots, the modern day robot should be capable of parallel processing and mimic the capability of a human brain. This is when the idea of neuromorphic architecture comes into picture. In case of neuromorphic computing, the memory and processing takes place at the same position, which minimizes energy consumption, latency, and increases the data handling capacity. This is a simple schematic of human brain. We all know that human brain is composed of 10 raised to the power 11 neurons, which are interconnected through 10 raised to the power 15 synapses. The presynaptic neuron receives sensory information as X1, X2, X3. Then the signals from the presynaptic neurons release ions in the form of neurotransmitters, which directly control how strongly the postsynaptic neuron responds. The input signals as X1, X2, and X3 are locally stored and weighted and integrated at the synapse, analogous to the weighted sum operation, that is WIXI, used in the neural networks. In this paper, in collaboration with Cambridge and Harvard University, Samsung has experimentally demonstrated that memory and computation are localized at synapse in human brain. Here, a CMOS nanoelectrode array, or in other words, large number of vertical nanoelectrodes are fabricated over silicon wafer. Then rats, alive neurons, are cultured over these steps. Then a small magnitude of current is passed through these nanoelectrode array, which results in the creation of a small hole in the neuron's membrane and establishes a connection of the nanoelectrode array with the membrane. Now, these nanoelectrodes are used to record the action potential, that is when a neuron fires, and postsynaptic potential, which are the signals from other neurons. For example, neuron A fires and shows a large voltage change. Then after some time, say 25 milliseconds, neuron B shows a small voltage change and this process repeats several times. This shows that neuron A is connected to neuron B. Neuron A fires and neuron B receives. Also, here, when a presynaptic neuron fires, the postsynaptic response is determined by the existing synaptic strength, meaning that the signal processing occurs exactly where information is stored without any separate processing unit or data movement. This data is digitally recorded as voltage and time for 19 minutes, and then the rat's neurons are removed from the nanoelectrode array. Then the stored information is extracted by computer-aided analysis to synthesize a memory network with 1000N memories. There are many neuromorphic inspired CMOS chips, namely SpineAcre 2, Loy 2, IBM North Pole, and BrainChip Akida Pico, that enable real-time event-driven synaptic neural network processing with sub-millisecond latency and drastically improved energy efficiencies compared to the GPUs. In this slide, I'll discuss about the challenges motivating memristors and 2D materials. Due to present-day technological needs, many companies, startups, and universities are actively working on neuromorphic computing and sensing and showing a strong collaboration between industry and academia, driving brain-inspired hardware development. As a result, the global neuromorphic computing market is expected to increase to 29.2 billion USD by 2032. However, these neuromorphic chips, which I also mentioned in the previous slides, are facing few challenges. First is they are based on conventional CMOS technology. We all know that human brain has 10 raised to the power 11 neurons connected with 10 raised to the power 15 synapses. So, to match human brain efficiency, a high density of device integration is required, and this is not possible with conventional silicon-based semiconductors as beyond a certain technological node, they face technological issues such as high leakage current and power consumption. Further, downscaling conventional CMOS devices is cost expensive and also very technological complex. These challenges demand adoption of new materials, that is 2D materials, and a new device architecture, which is memristor, which I'll discuss in the next slide. Now, memristor is a simple two-terminal device whose resistance depend upon history of electrical current or voltage passed through it. They are similar to human brains because they behave like synapses. Their conductance change depends on the past electrical activity, just like synaptic strength changes with neural signals. Now, there are various advantages of 2D materials over bulk CMOS materials such as silicon. 2D materials are basically referred to as materials which have one dimension less than de Broglie wavelength of electrons. There are several importance of 2D materials over bulk, such as they lack dangling bonds which help them maintain pristine defect-free interface and also mitigate surface scattering. Second is they have better carrier confinement which helps to maintain a better charge localization. Also, they have a better control over the channel area due to atomic thickness which helps to reduce the leakage current. Inspired by this, in my research work, I am working over wafer scale synthesis of 2D material, which is boron nitride, using low pressure chemical vapor deposition and use it for its memristive properties. The research results can be looked in detail in my recently published article entitled Synthesis of Amorphous Crystalline Mixture Boron Nitride for Balanced Resistive Switching Operation. I have basically synthesized large area boron nitride films of controlled crystallinity using LPCVD setup by using aminoboron as a reaction precursor and copper foil as the growth substrate. This is the corresponding optical microscopic image of the as-grown boron nitride film after being wet transferred over SiO2 substrate. This is the corresponding low resolution TEM image with the corresponding EDS maps of boron and nitrogen atoms. This is the corresponding X-phase spectra and the Raman spectra of the as-grown boron nitride film. As evident from the high resolution TEM images and SED images, you can see I have synthesized boron nitride film with varying ratios of amorphous and crystalline boron nitride, varying from 10:0 to 7:3 to 3:7. Then I have used these films for comparison with human eye through recognition of Zephyr images as discussed in the next slide. I basically fabricated an array of memristor over my as-grown boron nitride films of mixed crystallinity as well as amorphous nature. This figure shows the long-term potentiation characteristics of the boron nitride film. The nonlinearity factor, that is beta, is a critical parameter that determines the learning accuracy of neural networks, where a lower value of beta corresponds to a higher accuracy. It is found to be 4.8 for amorphous film, whereas 1.4 for a mixed crystallinity boron nitride film. Then based on these long-term potentiation characteristics, we performed training and classification tasks using the CIFAR-10 images dataset, and we found that mixed crystallinity boron nitride film exhibited a learning efficiency of 87.26%, whereas the amorphous boron nitride exhibited a learning efficiency of only 68.86% compared to the ideal scenario of 88.87%. So in conclusion, I can say that boron nitride based memristor array was successfully fabricated, demonstrating performance comparable to that of the human eye. This is why I believe and I can strongly say that my research is important. Now I'll discuss my future plan. So my future outlook will be to integrate boron nitride memristor arrays with near sensor computing to enable real-time image recognition with reduced power and latency. furthermore, to enable on-chip learning where the memristor's weights are updated in real time to adapt and improve recognition. And with this, I conclude my presentation. Thank you for your time and patience.